Okay, so we're going to talk about derivatives of inverse functions. So I'm going to start with just talking about what an inverse function is and how to find it and all of that. So this may be a review for some of you. Let's go in here and just jump right into it. Suppose that we start with a function f of x, and if f of x is 1 to 1, and what that means is that no two x values lead to the same y value, then we may find the inverse function, which essentially just reverses what the f of x function does. In other words, if I start with some value over here, x, I plug it into the function f of x, then I get a value that comes out of it. We usually call that y. Then if I take this value over here and I plug that into the inverse function, that ought to take me back over here to the value that I began with. And so let's see, how do we find an inverse first of all? I'm going to rewrite this here. I've got f of x equals negative 1/3 x plus 5. I want to find the inverse, and I'm going to rewrite this as y equals negative 1/3 x plus 5. So all I did here was just put a y where the f of x is. To find the inverse, essentially what we're doing is we're just interchanging the roles of x and y. So I'm going to just write down an x over here where the y is, and I'm going to write down a y where the x is. And then I'm going to solve this thing for y. So I've got x equals negative 1/3 times y plus 5, and I'm going to solve it for y. Let's see, if I multiply everything in here on both sides of the equation by negative 3, that would get rid of the negative 1/3. So I would end up with, let's see, negative 3x equals y. Negative 3 times 5 gives me a negative 15. And so if I add 15 to both sides, I get negative 3x plus 15 equals y. And essentially, I found my inverse function here. This, I'm going to rewrite using my inverse function notation, but this is just f inverse is equal to negative 3x plus 15. And the claim is that this is the function that will undo what this one up here does. All right, so if f of x equals negative 1/3 x plus 5, then negative 3x plus 15 will undo that. So let's play around with that just a little bit. I want to go in here and I want to show that f of f inverse is equal to x, where I've got these two functions that are inverses of each other. I mean, it should. If I take this thing and I plug it back up here into this function, then I'm just completing this entire circuit and kind of ending up right back over here where my x is. So let's see, does it do this? Okay, so I'm looking at the composite function here, f of f inverse of x. Well, that would just be f of, let me see, the inverse is negative 3x plus 15. So that's what's getting thrown into the f function. And the f function is negative 1/3 x plus 5. So I'm just going to put negative 3x plus 15 where the x is here. So that is negative 1/3 times negative 3x plus 15 plus 5. Don't forget the plus 5 hanging out there. Okay, so let's multiply the negative 1/3 inside the parentheses. It looks like that would give me x minus 5. And then I've got this plus 5 out here. Now the 5's cancel out. Looks like I've got x. And so it does exactly what I expected it to do. And in general, that's a property of inverse functions, is that if you took the composite, then what you get is you just get x. If f of x and g of x are inverses of each other, then f of g of x is equal to x. And by the way, we could write that the other way around. It could be g of f of x equals to x. Either way, it works. So we've got this. This is a nice little equation right here. In fact, it's nice enough that I'm going to rewrite it. F of g of x is equal to x. And we just saw that like right up here in this other example. So hey, this is a calculus class. How about if we do something like derivatives? Let's take the derivative of both sides of the equation and see what do we get. Well, the right-hand side's really easy, right? The right-hand side, the derivative of x will just be 1, so we're not going to worry about that. But what about the left-hand side? I've got a function inside of a function here. And I've got a rule that tells me how to deal with those types of derivatives. That's called the chain rule. And so the chain rule says hey, just take the derivative of the outside function, but make sure you multiply that by the derivative of the inside function. So let's do it. Let's take the derivative on both sides. The chain rule is going to tell us to take the derivative of the outside function. So that would be f prime of g of x. That's the outside derivative. And then multiply that by the derivative of the inside, which is g prime of x. That's coming strictly from the chain rule. Outside derivative times the inside derivative. And on the right-hand side, take the derivative over here, you just get 1. And okay, fine, that's a nice little formula. It involves derivatives. But really what it does is it allows us to find derivatives of inverse functions in terms of a derivative of the original function. If I solve this thing for g prime, I get g prime of x equals 1 over f prime of g of x. And what that means is that, hey, suppose that I had some really complicated inverse function. I started with some function f, and I know how to find the derivative of that. It's not too hard. But then when I find the inverse of it, that inverse turns out to be pretty complicated. Then what this allows me to do is find the derivative of the inverse in terms of the derivative of the original function. Okay, so that's fine. I'm going to show you an example. It's not real complicated, but I'm going to show you an example of us using this. And then we'll go on to see where do we actually use this in different applications. I want to find the derivative of g of x equals the square root of x. Now, I know how to do that derivative. That's the g of x equals the square root of x. This is x to the 1/2. Bring the 1/2 out in front, subtract the exponent by 1. I could find that derivative directly, but let's just use this technique. Let's just see how this works. Okay, so g of x is equal to x to the 1/2. When I know I need to find the derivative of that. Let's see. The inverse of x to the 1/2, the inverse of the square root function is the square function. So that's f of x. All right. I know that g prime of x is equal to 1 over f prime of g of x. Okay. That's the formula that we just came up with right over here. Okay. So let's play with this a little bit here. F of x equals x squared, so f prime of x is equal to 2x. Pretty easy. And f prime of g of x, its composite function, would be 2. Now I need to stick whatever g of x is in here, place where the x is. Well, g of x is x to the 1/2, so this would be 2x to the 1/2. And so my derivative right over here, g prime of x, is 1 over 2x to the 1/2. And we got it. And so, yes, we could have gotten to this directly just by taking the derivative of g of x, but we see that the process works. And it allows us to find derivatives in terms of their inverse functions. And one of the ways in which this is actually used is when we go into some of these more complicated functions, inverse functions, such as the inverse trig functions. So what I want to do here is I want to just go into an example. I want to find the derivative of g of x equals arctangent of x. Okay, so this is the inverse tangent function over here. And let's just remember for a moment, what is this? Remember, arctan is an angle. It's the angle that if I take the tangent of that angle, I get the value x. So I want to find the derivative of the inverse tangent of x, the arctan x. Well, I don't have any kind of formulas or anything for that, at least not yet. But one thing I do know is that the inverse of g of x, the inverse of the arctan function, is the tangent function. F of x equals tangent of x. So now let's go in here. If I can find the derivative of tangent of x, then I should be able to write down at least some kind of formula for the derivative of arctan x. Well, you may know this. You may have a formula that you just kind of wrote down or something, but this isn't too tough. The derivative of tangent of x, well, this is just, what, sine x over cosine x. So take the derivative of that. If I use the quotient rule here, let's see, this would be the derivative of sine x, which would be cosine x, times the bottom, which would be another cosine x, minus the top, which is sine x, times the bottom, times the derivative of the bottom, which is negative sine x. Okay, all that over the bottom squared, so cosine squared of x. Okay, and I think you can see that the top up here is just cosine squared x, got two negatives here up here, so that's plus sine squared x up there on the top. And I got a cosine squared x down here in the bottom. And remember, this is one of the Pythagorean identities right here. Cosine squared plus sine squared is equal to 1. And so I got 1 over cosine squared x right here. And I know that that's the same thing as, I'm running out of room here, but that's the same thing as secant squared x. Okay. So, fine, the derivative of tangent of x is secant squared x. And so, yep, I should be able to go ahead and find the derivative of arctan x. And let's do that here. So the derivative of arctan is, and I'm just using my formula, right, 1 over f prime of g of x. All right, so that would be f prime. I just found that f prime is equal to secant squared. So that would be 1 over secant squared of g of x. Now let's remember that g of x is the original function. G of x is arctangent. And okay, fine. I've now found the derivative of arctangent. And it's a formula over here, and it's, really there's nothing all that wrong with this, except for the fact that there's something more. It seems like there's something more I should be able to do here. Remember, arctangent of x is an angle. So taking the secant of that angle should be possible, and squaring it to get, that squared answer there. I should be able to get something for this. And so maybe we can go in here and simplify this a little bit. I'm just gonna do this. Remember, arctangent is an angle, so I'm gonna write that down as I'm gonna call it alpha. Okay, so I know that if I take the tangent of the angle alpha, then I should get the value x. All right. So I'm gonna write alpha over here as an angle. Okay, I'm just using a nice little right triangle. And I know that the tangent of that is x. And remember that tangent is opposite over adjacent when you're dealing with right triangles. And so I know that tangent of alpha should give me x, and I can kind of put whatever numbers I want to in here. It's the ratios that are important. So I'm gonna just make this as simple as possible. I'm going to let this be x over here, and I'm going to let this be 1 down here, and now I know that opposite over adjacent, x over 1, is going to give me, the tangent of alpha would be x over 1, which is x, which is what I was looking for. But, okay, fine. What this means is that I should be able to go in here and find any of my other trig values. I should be able to find sine of alpha and cosine of alpha. And if I can do that, then I should be able to find secant of alpha, right? And remember, alpha is arctan x here. And so remember what I need to do is I need to find all 3 sides. If I have a right triangle and I've got 2 sides, I can find the other one here just using the Pythagorean theorem that says that this squared plus this one squared is equal to the hypotenuse squared. So I know that 1 squared plus x squared is equal to the square of the hypotenuse over here. So taking the square root of that gives me the square root of 1 plus x squared. All right. And all I did there was just sort of c squared equals a squared plus b squared type of thing, and then just solved it for c. But that allows me to go in here and find other trig values. In particular, let's remember, I don't know if you remember what secant is, but cosine is usually one that we remember. Cosine is adjacent over the hypotenuse, okay? And which means that cosine, if I look at the reciprocal of that, I get secant. So that I know that secant is hypotenuse over adjacent. Okay, so secant of alpha, which remember is secant of arctan x, is hypotenuse over adjacent. So that would just be the square root of 1 plus x squared, right? Hypotenuse over adjacent. All right? Which means that if I go all the way back up here, then secant would just be the square root of 1 plus x squared. So secant squared would be just 1 plus x squared. And it looks like I should be able to go ahead and write down now, right, g prime of x, which is arctangent of x prime, is, I've already written down, 1 over secant squared arctangent of x. And I just found that secant of arctangent of x is the square root of 1 plus x squared. So this would be 1 over 1 plus x squared, the square root of that, but squared, right? Because that was secant squared. And it looks like that ends up giving me 1 over 1 plus x squared. All right, and so I've found the derivative of this trig function. And I know that's a little complicated. Yeah, we went through and used some trigonometry and all of this kind of stuff, but I hope that you could follow through that and you can see that, okay, this isn't really too tough of a formula over here. Arctangent of x, if you've got this and you're trying to find the derivative, you just get 1 over x squared, and it's not too tough. But, okay, now that we've done that, you can see that would work whether I was dealing with arctangent or arc sine or arc cosine, or I could even do the reciprocals. I could do arc cosecant, arc secant, and all those kinds of things. And so I've really just written these things down. To find each of these things, we just go through that same type of procedure, and we end up with these formulas right here. I think it's best for you to kind of write these down somewhere. Just kind of think of these as like little templates here, okay? If you need the derivative of something involving arc cosine, then remember, hey, this is the derivative of that, and then you go on to use that into whatever else you're doing. Once you've got these formulas, now we can use these in the different rules, right? When you're doing product rules and quotient rules and the chain rule and all that, now that we know what these derivatives are, we can use them. So let's look at some examples of that. I want to find the derivative of f of x equals arctangent of 4x cubed. Okay, so I've noticed here I've got a function inside of a function, right? So I'm going to use my chain rule sort of in the traditional sense here. Function inside of a function. Take the derivative of the outside function. So your question is, okay, do I know how to find the derivative of arctangent? And the answer is yes, we just did it. And we've got a formula for it. So I know the derivative of arctangent is 1 over 1 plus x squared. All right, so let's do it. Let's go in here and find this. F prime of x is equal to the derivative of the outside function. That would be 1 over 1 plus. Now remember, I'm not going to put x squared here. I'm going to put my g of x. I'm going to put this in here. So 1 over 1 plus 4x cubed squared. That's the derivative of the outside. And then multiply by the derivative of the inside. Well, after all of this inverse trig stuff, hey, I'm looking forward to an easy derivative. That's just going to be, what, 12x squared. There we go. And we're done. Basically, we're done. The only other thing here is maybe clean it up a little bit. Looks like I could write that as 12x squared up here in the top. 1 plus, okay, I could clean this up a little bit. 4 squared would give me 16. And x cubed squared will give me an x to the 6th. really nothing else I can do there. I found that derivative. Well, what about this one? I want to find the derivative of arc cosecant of the square root of x. You know, when you look at this, at first it may seem a little intimidating. Oh, wow, I've got arc cosecants and I've got the square root of x in here. But remember, this, when taking the derivative of this outside part right here, we've just got a formula for that. We're just going to go over here and see what that is. So so maybe before I do that, let me rewrite the problem a little bit. I'm not doing the derivative yet. I'm just going to go ahead and write this as arc cosecant x to the 1/2 because I know I'm going to have to take the derivative of that inside part. So I'm just doing that. Now let's do the derivative here. Let's see. Function inside of a function, which means I've got to think about my chain rule. So the outside derivative, okay, I'm just going to cheat over here and get my formula. Looks like the derivative of arc cosecant is -1 over the absolute value of x times the square root of x squared minus 1. All right, so that would be -1 over the absolute value of this thing right here, right? So that's x to the 1/2 times the square root of x squared, so again, x to the 1/2 is what's going in there, squared minus 1. All right, and that's the derivative of the outside part. And I just used my formula here. Don't feel bad about using the formula. Everybody, I've been doing mathematics for 30 years. I still look up these formulas for the trig, inverse trig functions. So just go over here, use your formulas. We've got the outside derivative part done. And now we're going to multiply here by the derivative of the inside. Well, okay, after all of that, the derivative of the inside should be pretty easy. So that looks like that's just x to the 1/2. I get a 1 over 2. That would give me an x to the -1/2, which I'm going to go ahead and bring down here. Okay? And really, you know, I could clean things up a little bit here. I've got, let's see, a -1 up here. X to the 1/2 inside of an absolute value. And let's see, I've got the square root. X to the 1/2 squared would just give me an x minus 1. I've got a 1 over 2 x to the 1/2. I might could do a little bit more here. If I know that I'm only dealing with the real number system, then I know that that this right here would have to be something positive, you know. But if I which means I could kind of get rid of those absolute values and maybe combine that x to 1/2 with this one. But you know, if I don't know for sure I'm dealing in the real number system, these may be imaginary numbers, and so the absolute value would play a different role there. So I'm just going to leave it as it is. It's perfectly fine like that, and I'm going to move on. Well, maybe here we go. We're going to get to the example you've been waiting for. That is the last one. So the derivative of f of x equals 2x squared times arc sine of x. And so I want to find this derivative. Well, what I notice here is that I've got a product. Right? I got this part here times this part here. And so I'm going to use my product rule. F prime of x is equal to u prime times v plus u times v prime. And should be pretty straightforward here. U prime, that would be the derivative of 2x squared. That's just going to give me a 4x. V is just arc sine. I'm not doing any derivatives there. I'm just going to write down times arc sine x plus u, which is 2x squared, times v prime. So now I'm taking the derivative of arc sine, and I'm just going to go over here and look at my formulas. The derivative of arc sine is 1 over the square root of 1 minus x squared. So this times 1 over the square root of 1 minus x squared. I don't see a whole lot of simplification that we could do there. Looks like a perfectly good answer. All right, so that's the end of the video. I hope this has been helpful. Best of luck to you.